Hey, welcome back to our second topic in Unit 5. Today we're going to talk about the extreme value theorem, global and local extrema, and critical points. Okay, we'll jump right in here talking about extrema of a function. In calculus, much effort is devoted to determining the behavior of a function f on some interval I. These things that we're looking for, such as maximum and minimum values, increasing and decreasing, are just some of the things we're going to take a look at as we get further into this chapter. Okay? We will use derivatives to answer these questions and many more and then apply them to real-life situations. A function does not have to have a maximum or a minimum on an interval. For instance, in figure 1, the function has both a maximum and a minimum. So we have a maximum point up here and a minimum point down there, right? But in figure 2, even though we still have a minimum, there is no maximum. It might look like we do have a maximum, but there's a hole there. So this function will continue to get closer and closer and closer to 5, but never actually reach 5. So we don't have a maximum. Same can be true here about this third one. The maximum is back, but the minimum has a hole. So again, this function will never actually reach the minimum value of 1, so we say it has no minimum value on this interval. And that brings us to the extreme value theorem. If f is continuous on a closed interval, then it has to have both a maximum and a minimum on that interval. So this function, not continuous because of the jump right here, the little hole, the removable discontinuity. This function, not continuous at the endpoints. This function is continuous the whole time, which is the only reason why it had to have a minimum and a maximum value on that interval. Okay, you can see there we have a couple examples of extrema. Basically, we're talking about either really high points, such as mountains, or really low points, such as valleys, or the trench in the Pacific Ocean. Okay, those are extrema in the real world. So let's talk about relative extrema and critical numbers. So here we have the graph of x cubed minus 3x squared. It has a relative maximum here and a relative minimum here. The word relative, okay, means basically compared to the numbers around it, okay? So think of the relative maximum as being a peak of a mountain on the graph and the relative minimum occurring as a valley on the graph. Note that the peaks and valleys have smooth, rounded curves about them. Then the graph has a horizontal tangent line at those points. Note that at each relative extrema, the derivative is either going to be 0 or it does not exist. Okay, now obviously in both these cases it's going to be 0. The x values at these special points are called critical numbers, and these are critical to your knowledge in calculus moving forward. Okay? How do we find critical numbers? Let the function f be defined at some x value c. If the derivative of f at c is 0, or the derivative of f at c is not differentiable, so the derivative of f doesn't exist at c, then we call c a critical number of f. Definition of relative extrema. Again, we have that function whose second derivative exists on an open interval. If there's an open interval containing c on which f of c is a maximum, then f of c is called a relative maximum. And the same is true for a relative minimum. Okay. By the way, the plural of maximum is maxima, and the plural of minimum is minima. So if there's more than one maximum, then you say there are maxima. Here are some examples of a critical number c of a function f. We have a critical number right here because the derivative does not exist because of the cusp. So that c we call a critical number. We also have a critical number here because at c, the derivative is 0. So those are critical numbers on these graphs. There's a very important statement right here that relative extrema will only occur at critical numbers. Okay? It's very important for what we're going to get through in this chapter that we understand that. So if f has a relative minimum or relative maximum at c, then c has to be a critical number, which means either derivative is 0 or doesn't exist at that point. All right, let's take a look at a couple problems here. First one says if f is continuous for a to b and differentiable for a to b open interval, which of the following could be false? So the first one that is the mean value theorem that we just talked about in our last lesson. That one has to be true if the function is continuous and differentiable. The second one, the derivative is 0 for some c such that a is less than c is less than b. All right? That one does not necessarily have to be true. That's Rolle's theorem, okay? That could be true if f of a and f of b were equal, but doesn't have to be true. So that's probably going to be our answer. Let's double check C and D. C has a minimum, F has a minimum value, D, F has a maximum value. Well, we already talked about this earlier today. By the extreme value theorem, or people call the EVT, if the function's continuous on an interval, it has to have a maximum and a minimum value on that interval. So these are both true by EVT, and this is true by MVT, which means B is our one that could be false. It could also be true, but it could be false. Number 2, the function f is defined in the closed interval 0 to 1 and satisfies f of 0 equals f of 1/2 equals f of 1. On the open interval 0 to 1, f is continuous and strictly increasing the whole time. Which of the following statements is true? All right, so looking at statement A, f attains both a minimum value and a maximum value on the closed interval 0 to 1. Statement B, f attains a minimum value but not a maximum value on 0 to 1. Statement C, f attains a maximum value but not a minimum value on the closed interval. And D, f attains neither a minimum nor a maximum value on the closed interval 0 to 1. Okay, so if you take a look at this problem here, it's a little bit of a confusing problem, but it says that the function f is defined on the closed interval 0 to 1, but on the open interval, f is continuous and strictly increasing. It doesn't say it's continuous on the closed interval 0 to 1, so this is the key to this problem right here. Okay, if it was on the closed interval, then we would know that yes, we have both a maximum and a minimum value on this interval. But because it's on the open interval, we don't know if it has a maximum or a minimum on this interval. So let's take a look at what a graph of this might look like. We don't know what f of 0 is, but let's say f of 0 is 2. All right, f of 0 is 2. That means f of 1 is also 2, and that means f of 1/2 is also 2 because of this right here, right? But on the open interval, f is always increasing, so f itself would have to look something like this. So if you take a look at that, we can clearly see that f would have neither a minimum nor a maximum on this interval. No minimum, no maximum, which means D is our answer. Question 3, let g be a function given by g of x, where k is constant. For what values of k does g have a critical point at x equals 3/2? All right, so to get a critical point, we got to take the derivative and set it equal to 0 or undefined. So let's take our derivative. We have x squared times ke to the kx plus 2x times e to the kx. Okay? We know x is equal to 3/2, so if we put 3/2 in here, let's see, we would get 9k over 4 e to the 3k over 2 plus 3e to the 3k over 2. All right, and then we're going to set that equal to 0 or undefined. Well, that's never going to be undefined, so don't got to worry about that, but we can set it equal to 0. All right, solving this can be a little tricky. Why don't we first subtract the 3e to the 3k over 2 over, so we get negative 3e to the 3k over 2 equals 9/4 e to the 3k over 2, sorry, 9k over 4. All right? And if we multiply by 4/9 on both sides, we would get negative 12 over 9, or negative 4/3 e to the 3k over 2 equals e to the 3k over 2. And perhaps we've been better off if we didn't bring this over to the other side. But I'm going to end up bringing it back anyway. So I get e to the 3k over 2 plus 4/3 e to the 3k over 2. And now if we factor out an e to the 3k over 2, I keep forgetting this k over here. Sorry, there should be a k right here and also right here. Now we're left with k plus 4/3. This could never be 0, but this can be 0. So k plus 4/3 equals 0, and therefore k is equal to negative 4/3. And that would be our answer A. All right, the last thing we're going to do here is we're going to practice finding some critical numbers of functions. So again, remember, a critical number comes when a derivative is either 0 or undefined. So let's take our derivative of A, and we want to set that equal to 0 or C when that would be undefined. Now that's just a cubic function. That will never be undefined, but there's a good chance it will equal 0. So if we set the first part equal to 0 and the second part equal to 0 individually, we'll get 3 critical numbers. So our 3 critical numbers here are -1, 0, and 1. What does that mean? That means that those 3 numbers could possibly be relative extrema. They don't have to be. We'll take a further look into this in the next couple of sections here, but they have the possibility of being critical of relative extrema. Let's take a look at our last one here. So again, take our derivative. And if we rewrite our derivative, so again, a critical point can be when the derivative is either 0 or undefined. This derivative will never be 0, because if you set 0 equal to this, and then multiply both sides by x and 1/3, you get 0 equals 2, which is not possible. But it definitely could be undefined when the derivative is equal to 0. And that's just going to be when x equals 0. So x equals 0 is the only critical point for this function. What that means is that at x equals 0, that function may have a relative extrema, or it might not. We'll learn how to prove if it does or doesn't in the next few topics. That's it for our lesson today on critical points, relative extrema, and the extreme value theorem. Thanks again for checking out my video today, everyone.